Okay, in this lecture we are going to study Dijkstra algorithm. Okay, as I mentioned earlier, Dijkstra's algorithm is a shortest path algorithm for graphs all of whose edge weights are non-negative. You can have cycles, but all the edge weights of the graph are going to be non-negative. So negative edges are not allowed in the graph. So no negative edges. Okay, and this is very natural in some situations. What are these situations? Well, the situation is going to be, well, it's going to be natural when edges are physical quantities like distances, time, queue size, queue size, and so on, which can only take non-negative values. Okay, and given that, it's going to be important. And finally, the algorithm is a greedy algorithm, and it's going to share a lot of commonalities with Prim's algorithm. All right. Okay, so let us understand how Dijkstra's algorithm works. Okay, so basically, here is what Dijkstra's algorithm does. Think of it as exactly, there is many ways of thinking of it. One way of thinking of it is think of it as an algorithm that's very much like Bellman-Ford. Okay, but what we are doing is every edge is relaxed exactly once. Okay, so whereas in Bellman-Ford what we would do is we would come up with an order of edges E1, EM, and then relax n minus 1 times, where n is the number of vertices. Okay, so this is original Bellman-Ford. Okay, whereas this is original Bellman-Ford. In Dijkstra, I'm going to choose or compute a clever ordering of edges. Okay, so I'm going to compute a clever ordering of edges somehow, and just relax edges according to order. And if I do so, I just need to do one relaxation for every edge, and that's it. All right. Now, how do we do this? So here is the idea. So just like Bellman-Ford, Dijkstra is going to maintain for every node, it's going to maintain what? So it's going to maintain for every destination the current distance estimate and a parent. And it's going to start with the source, initialize it to 0. Parent, of course, for the source is not defined. Everyone else is going to start with infinity and undefined parent. Okay, so here is the idea. Here is the idea. At every step, choose choose a previously unvisited node. Okay, choose a previously unvisited node, number 1, whose d value is smallest. Okay, so at every step, choose a previously unvisited node. So originally everything is unvisited. Okay, and idea is choose a previously unvisited node whose D value is the smallest. Do that at every step. Okay, number one. And number two, okay, and number two, relax. So let us call this a node V. Okay, relax all outgoing edges of V, mark V as visited, and do this until all nodes are visited. That's it. Okay, so what is the algorithm? Algorithm is until all nodes are visited, do this. Okay, what is this? Well, choose a previously unvisited node whose D value is the smallest. Okay, so this is it. Relax all outgoing edges of V, mark V as visited. Okay, so these are the 3 steps of the algorithm. So let us do this on an example. Okay, keeping this algorithm here, let's do this on an example. Okay, so here's an example with 7 vertices, and a bunch of edges that I've shown with edge weights. Okay, and just like Bellman-Ford, I'm going to initialize a table of for every vertex. I'm going to record the D value, the parent pi. So far it's going to be 0 for the source, infinity for everyone else, the parent's going to be nil, and I'm going to track whether the node has been visited or not, false or true. Okay, so first nothing has been visited, and let's keep 1 as the source as usual. All right, with that said, how does the algorithm start? Here it is. Until all the nodes are visited, at every step choose a previously unvisited node, so visited must be false, with D value being the smallest. Which node is that? So in the very first step, I'm going to choose the node 1, whose D value is 0, which is the smallest. So I'm going to choose the node 1. Relax all outgoing edges of V. So relax all outgoing edges of 1. When I do that, I relax 1 to 2, I relax 2 to 3. Okay, I relax 1 to 2, I relax 1 to 4. Okay, now what happens after I relax? Well, the value of the node 2 is going to become, and the value of the node 4 and their parents are going to get updated. What are the values? The value of the node 2 is going to become, the distance estimate is going to become 1, the value of the parent is going to be 1, the distance estimate for 4 is 2, the value of its parent is 1. Okay, and mark the vertex V as visited. So mark the vertex V as visited. All right, so then that's done. What's the next step? Well, again, let's keep doing until all nodes are visited. Are all nodes visited? Not yet. So the next step, choose a previously unvisited node V whose D value is the smallest. Which is the node with the smallest D value so far? Well, the answer is the node 2. It has the smallest D value among all the nodes which are as yet unvisited. All right. Now, choosing 2, relax all its outgoing edges. So relax 2 to 3, 2 to 5. So what do we get when we relax 2 to 3? Well, the weight of vertex 3 is going to become, okay, so weight of vertex 3 is going to become 1, its parent is going to become 2. 2 to 5, the weight of vertex, weight of vertex 3 is going to become 2 and its parent is 2. Weight of vertex 5 is going to become 1.5. And its parent is going to become 2. All right, good so far. All right, so now that this is done, I'm going to set 2 is true. All right, what's the next one? Well, the next one is going to be choose the smallest that has not yet been visited, and that is vertex 5, which has a weight of 1.5. All right, so we choose vertex 5 and we relax the outgoing edge for vertex 5. which is going to be 5 to 4. So when I relax 5 to 4, the weight for 4 gets updated. Okay, so the weight for 4 gets updated. And what's the weight for 4? Gets updated to 1.7, and its parent gets updated to 5. Okay, that's good. All right, so the weight for 4 gets updated, its parent gets updated. All right, good. And then 5 is now visited. True. All right, so good so far. Okay, what's the next one? Well, the next one is 4, whose weight is 1.7. Well, so the outgoing edges for 4 get relaxed, which are going to be 4 to 3 and 4 to 6. So when I do 4 to 3, its value gets, 3's value gets to 1.7 plus 1, so 2.7, but it's already 2, so I'm not going to touch it. How about 6's value? 6's value is going to become 1.8, and its parent is going to become 4. Okay, now 4 is done. All right, what's the next one? That's going to be 6, which is the smallest so far, okay, among all the unvisited nodes. So now I'm going to relax 6 to 2. Okay, so when I relax 6 to 2, 2 is already been visited, so there is not much I do. I'm not going to bother. All right, what's next? Next is going to be look at all the nodes that are not so far visited. Okay, and that just leaves us 3 and 7. So 3 is going to be the next one that's chosen, and I'm going to relax its outgoing edge. So I'm going to relax according to 3 to 6. 3 to 6 is going to try and update the weight for 6 to 2.5, but 6 has already been taken care of with 1.8, so nothing more needs to be done. Last but not least, I'm going to take 7 and relax all its outgoing edge, but when I try to relax the edge 7 to 4, there is no effect, so this is also done. And then all nodes are visited. And therefore done. Okay, in doing so, notice that I visit every node once. I visit every edge exactly once and relax along it. Okay, so this is going to be quite efficient compared to Bellman-Ford, right? So every node is being visited once, and plus every edge is being visited once, right? When I visit a node, I relax according to all its outgoing edges. But there is a key step. What do I need to do? At every step, I need to find a previously unvisited node V whose D value is the smallest. So I need to go through all the nodes and choose the one whose D value is the smallest. How do I do that? Is there a data structure that we have learned so far? A data structure that is efficient for maintaining minimum key. Have we learned such a data structure? Can you think of it? Yes, we have. And the idea here is we can use a heap data structure. Right? If we use a heap data structure, according to the key, which is the D value of the node, then at every step, what you can do is among all the unvisited nodes, you can always find the smallest key value. Okay, so that is basically it. So we can now write the pseudocode for algorithm. Pseudocode. Here is the idea. Okay, so what's the idea? Let V be the set of vertices and E be the set of edges. let's have n vertices and m edges. Okay, first step is initialize for all vertices v. How do we initialize? If v is equal to the source vertex, then v dot d equals 0, v dot pi equals nil. Else, if it's not the source vertex, then v dot d is infinity, v dot pi is still nil. Okay, so that's the initialize. So this is the same as Bellman-Ford. All right, hopefully that's clear. Then the next step is to construct a heap. What does it mean to construct a heap? Well, let's make an array of all the vertices, okay, and heapify it using v dot d as key for vertex v. So v dot d is the key or the priority that I'm going to use. Okay, next step. All right, now comes the main loop. While q is not empty, okay, what do? Let me take a vertex u, which is going to be the minimum vertex in the queue. Let me extract the minimum vertex. Okay, and then what? Once I extract the minimum vertex in the queue, let me iterate through all its outgoing edges. And how do I do that? I have an adjacency list, so I can take all the outgoing edges, v1 through vk. For all outgoing edges uv, what? Do the relax operation, but with a small caveat that I'm going to note for you. If u dot d plus the weight of uv is strictly less than v dot d, then what? V dot d must be equal to this quantity. Furthermore, v dot pi must be equal to u. Furthermore, remember that v dot d just decreased, so bubble up in the queue, bubble up v, because its key decreased, so you have to do this bubble up. And that's it. That is Dijkstra's algorithm in a nutshell. Okay, so this is the pseudocode for Dijkstra's algorithm. All right, what's the running time? Well, the initialization step runs as much time as the number of vertices. Heapify for n vertex is theta n. Outer loop runs n times. It goes through once for each vertex. What's the complexity of extract min? Well, theta of 1 to find the minimum element and theta of log n to do a delete. Okay. How many times does the inner loop run? Well, it's running as many times as the number of outgoing edges, but then for every vertex it's running as many times as the number of outgoing edges for that vertex. So sum of the number of outgoing for all vertex v, okay, sum of the number of outgoing edges for all vertex v is simply the number of edges in the graph m. So jointly, the outer loop and the inner loop jointly, if you take each time the outer loop runs and for that each time the inner loop runs, the total number of times this code gets executed is m times. And that's not surprising, as we noticed before, every edge is relaxed exactly once. But there is a hidden complexity here, and this is theta log n. So now if you add everything up, the total running time is theta n plus theta n log n coming from this step, which is running n times, plus theta m log n for this step. Okay, that is theta m plus n log n. much faster than Bellman-Ford because all the edge weights are positive. So now we are left with the question, why does Dijkstra work? Why does the algorithm for Dijkstra work? And I will treat that question in the very next lecture. See you then. Bye.